In today's talk, we're going to talk about generating functions. This is the subject for chapter G. Here's our definition. A generating function is just a polynomial, or in fact, we're going to be talking about generating functions which are power series, though our book sticks to finite degree polynomials, which has the property that the coefficient of the x to the k term is some number of combinatorial interest, so that we're going to be able to ask a combinatorial question and look at the coefficients on the different powers of x to get different answers. Here's an example. The function 1 plus x to the nth power, which you can recognize already as just a binomial expression, this is a generating function for the combination numbers. Why? Because the binomial theorem tells us exactly that 1 plus x raised to the nth power is precisely 1, which is n choose 0, plus n choose 1, x plus n choose 2, x squared, and we go all the way up to n choose n minus 1, x to the n minus 1, plus n choose n, x to the nth. This one I should have written it as n choose 0. So that if you look at the power of x squared, for example, the coefficient on that power, that second power of x, is precisely n choose 2. The coefficient on x to the kth power is n choose k. So this function, we say, generates these combination numbers. This is kind of looking at the exact same binomial theorem backwards. When we looked at it before, we were asking the question, what happens when we look at this expansion and we computed, in fact, that the combination numbers are what we get. Now we're saying, okay, let's talk about how we can generate the combination numbers, and voila, it's this exact binomial expansion. If we take a binomial expansion like 1 plus x to the 41st power, you wouldn't want to do that by hand. But here's the usefulness of generating functions. I can have a computer just expand 1 plus x to the 41st power, and you get exactly this. This is all done by my computer. No, I did not do this by hand. But let's take a look at this number here, 350,343,565. Since that's the coefficient on x to the 32nd power, I can tell immediately that 41 choose 32 is this number, 350,343,565. And if you go over here and look at x to the 9th power, which is here, of course you're going to see the exact same number there, because that's the same as 41 choose 9. Now, is this the easiest way to compute the combination numbers, the binomial coefficients? Of course not. But what we're going to see is we can actually take a combinatorial problem, create a generating function like this one, where the coefficients will give us the answers to the question we have, and then you can expand it either by hand, and we're going to learn some new techniques for that, or by computer, and then just read off the proper coefficients to get our answer. This is what's exciting about generating functions. So this is what I said we're going to do. Can we construct a generating function to answer other questions? And let's start with a simple question. Find the number of ways to select a 4-letter combination from the set ABC using at most 2 A's, 2 B's, and 3 C's. So we want a 4-letter combination. We don't care about order, but we want 4 letters. How can we do that? Well, we can do that in lots of different ways. We can take AABB, we can take AABC, we can take CCAB, lots and lots of different 4-letter combinations. How can we count them? Well, our first shot at that will be to form an algebraic expression like this. This 1 here we'll think of as a to the 0th power. Sorry about that. Get rid of that. This one, of course, we're going to think of as b to the 0th power. When we can choose up to, at most, 2 A's, which means we can choose 0 A's, 1 A, or 2 A's. I'm going to think of this expression, 1 plus A squared, as offering me a choice of which term to take when we expand this algebraic expression, if I use this term 1, that will be like using 0 a's. If I use the a, it'll be like using 1a. If I use the a squared, it will be like using 2a's. And I have the same choice for the b's. I can use either 0b's, 1b, or 2b. But for the c's, I can use either 0c's, 1c, 2c's, or 3c's. Now, what happens when I expand this? Well, any way that you choose a term here, and say a term here, in a, the a, the b, and the c squared, that will give me a term, abc squared. So there'll be a bunch of terms. One of them will be abc squared. And since I chose 1a, 1b, and 2c's, that will actually be a combination of length 4. In other words, a 4-letter combination. Now, some terms won't correspond to 4-letter combinations. Let's look at some other terms. If I choose this term here, that a squared, that b squared, and the c, I will have a term in this expansion, a squared, b squared, c, that will correspond to a 5-letter combination. So I don't want to count that term when I'm looking for 4-letter combinations. Well, what will mean I have a 4-letter combination? It's when the sum of the powers of a, b, and c total to 4, because the power of the a's is how many a's I take, the power of b is how many b's I take, the power of c is how many c's I take, and the sum of the powers is the total number of letters in my combination. So what I need to do is this. I need to expand this entire algebraic expression and then look for all of the terms where the sum of the powers is 4, and I'll get one of these combinations that I desire for each term. So I did that with my computer again, of course. 1 plus a squared times 1 plus b squared times 1 plus c squared plus c cubed is equal to this huge sum of all these different terms. And which ones have total power 4? You can just go through them and see. Here's one, a squared, b squared. That would correspond to the 4-letter combination with 2 a's and 2 b's. Where else do we have a total power of 4? There's an a squared bc. There's an a squared c squared. If we keep just scanning along here, we have an ab squared c. Here we have an abc squared. Here we have a b squared c squared. And as we keep going through, I think we're done. We skipped one. Here's a bc cubed. How many do we have? 1, 2, 3, 4, 5, 6, 7. I think we've still missed one. Whereas here's the ac cubed. There's another one. We have a total of 8 terms with the total power, meaning the sum of the power of the a, the power of the b, and the power of the c, of 4. That corresponds to 8 different 4-letter combinations from the alphabet A, B, C, where we're using at most 2 A's, at most 2 B's, and at most 3 C's. Now, this is a very laborious process. What would make things easier? Well, if I want to count all the terms where the total power is 4, here's a neat trick. If I replace all the a's, b's, and c's just by a single variable x, then a squared bc will just be x to the 4th. A squared b squared will be x to the 4th. A squared c squared will be x to the 4th. Each of these will be x to the 4th, and they'll have a term that looks like 8x to the 4th. So if I replace all of these letters by a single variable called x, then I just look at the coefficient on the x to the 4th term, and I'll get the total number of words. I'll get the total number of combinations that consist of 4 letters with our condition satisfied. Here's how we do that same example. Replacing the a's, b's, and c's by x's, we get this product here, 1 plus x squared times 1 plus x squared. This represented the a's, this represented the b's. And in both cases, we can choose either 0, 1, or 2 of them. And this represented the c's. We can choose either 0, 1, 2, or 3 of them. This is now a generating function that is used to answer this question. But not just the question of how many combinations there are of length 4, we can answer the question, how many combinations are there of length k from this alphabet with this exact same condition, And this will work for any number k. If I want to know how many combinations there are of length 3, I use this exact same generating function, but instead of looking for the coefficient of x to the fourth, I just look for the coefficient of x cubed. Let's just multiply this through. Here I used a computer to multiply 1 plus x squared times 1 plus x squared times 1 plus x squared plus x cubed, and I get x to the 7th plus 3x to the 6th plus 6x to the 5th plus 8x to the 4th plus 8x cubed plus 6x squared plus 3x plus 1. The fact that the coefficient on x to the 4th is 8 tells us the answer to our original question was 8. There are 8 combinations of length 4. But this tells me all these other answers as well. There are actually exactly 8 combinations of length 3 from the set ABC, with the same conditions that you have at most 2A's, 2B's, and 3C's. And if you want to know what they are, well, then you could go back here and just circle all the terms where the total power is 3. I won't look at all of them there. Maybe I will. There's one. There's another. There's another. There's another. There's another. There's another. Another. And another. Did I get 8 of them? 1, 2, 3, 4, 5, 6, 7, 8. All 8 of them. But this one generating function answers literally 8 different questions. Some trivial. How many combinations are there of length 0? The answer is 1. Just don't take anything. How many combinations of length 1? Well, there are 3. There's the A, there's the B, and there's the C. How many combinations of length 2? Well, you could take 2 A's, 2 B's, 2 C's, or you could take an AB, an AC, or a BC. You could easily list those. We already showed the combinations of length 3, and then up to the 4s, the 5s, the 6s, the 7s. You're not going to get combinations of more than 7 because we have at most 2 A's, 2 B's, and 3 C's. That's why the highest power of x that appears here is 7. If we change the question and say, what if we want to look for combinations of length 4 or any length k from the set ABC? Let's stick at this point with combinations of length 4. What if we have no conditions that restrict the number of A's, B's, and C's? Well, if we're looking for combinations of length 4, that gives us one restriction that we have at most 4 of any letter. Since if we're looking for combinations of length 4, you certainly can't use more than 4 of any letter. So for the A's, you'll have 1 plus x squared plus, here I seem to have made a bad mistake when I typed it in. So let me change all this. You would have an x cubed plus x to the 4th. So let me write that again. Our generating function would be 1 plus x squared plus x cubed plus x to the 4th. And then we would just cube it. And this generating function would tell you how many combinations there are of length 4 from the 3-letter alphabet A, B, C. No conditions whatsoever. And how would we do this? We would expand, and we would look for the coefficient on x to the 4th power. Now, you should remember that you can actually use things like the multinomial theorem to help you with this, but I'll leave that for you guys to play with.